Let's continue talking about Chapter 3. We're going to look at the properties of matter now. We're going to be comparing what are called physical properties and chemical properties of a material. So a physical property is any property of a material that is displayed without changing the composition of the material. Another way of saying this would be this is a property that you can measure, or you can identify, you can somehow quantize, if you want to say it that way, this property without changing the material itself. So taste, color, conductivity, odor, these are all things that you can measure. These are things that you could quantify without actually changing the material. So if you have a brick of gold sitting in front of you, because you are just rolling in it, apparently, and you look at that brick of gold, you will be able to identify, you will be able to measure, in a sense, or quantify the color of that piece of gold. I would assume it will be gold in color, since it is a piece of gold. And you didn't have to actually chemically change the piece of gold in order to measure that. Same thing if for some reason not only are you rolling in it, but you are also just kind of a bit weird and you decide to lick the piece of gold. You could tell how it tastes, and guess what? It's still gold. You don't have to you don't have to chemically change the material in order to measure a physical property. Density is the same way. You could take a piece of gold, you could weigh it to get its mass, you could then measure it to get its volume, and you can quantify the density, and it's still just a piece of gold. Melting points and boiling points are also physical properties. The reason for this is that even though they are changing in that they're going from one phase to another, it's still the same material. So the example that's given here, you have liquid butane in a lighter, and if you just press down on the little lever here so you don't strike the match portion here, you just push down on the lever. What it does is it opens the container so that the butane can start to escape, and the butane will instantaneously begin to go into the gas phase, and that is a physical change. It's a change that is due to a physical property that's being displayed, because it's still butane. It was butane here in the lighter, and it's butane when it's outside the lighter. It's just in a different phase. A chemical property, on the other hand, is displayed by changing the composition. So these things can only be measured, they can only be observed if they're actually chemically changing somehow. So, for example, flammability. If you're going to measure or observe the flammability of, I don't know, a napkin, maybe. You have a napkin and you want to figure out how flammable it is. You can't measure or determine its flammability by just looking at it and saying, yeah, looks flammable. Doesn't work. You have to actually set it on fire. You actually have to see how easily does this thing catch on fire. Can I just take a match and stick it next to it and then it bursts into flame? Or do I have to throw it into a fireplace where something's already burning before it will catch on fire? So if you're going to measure something like flammability, you actually have to chemically change the material. You actually have to light it on fire, which is going to then chemically change it. Same thing with corrosiveness or acidity, toxicity. These three are kind of similar in that if you're going to measure how corrosive a material is, so let's say you take some acid and you pour it onto a piece of wood, for example, and you want to see how corrosive that acid is, how quickly it starts to eat away at the wood. Well, in the process of eating away at the wood, it is actually chemically changing. The acid doesn't stay in its same chemical form before. The actual thing that's taking place is there's a chemical reaction between the acid and the wood, and that's what's causing it to be eaten away. And so chemical properties are displayed by changing the composition. A chemical change is where you start with one material and you end with a different material. Physical properties, again, on the other hand, they're displayed without changing the composition. So the example we have here of the chemical change is now we're doing the same thing we did before, but now we actually do hit the striker portion of the lighter, and so we still have the liquid butane that's escaping, but now instead of just escaping and going into the gas phase, it is burnt to produce this flame. And so that is a chemical change because it is displaying the chemical property of flammability. All right, and there are some more examples in the book if you want to look at those. But moving on, when we're looking at chemical changes that are taking place, there's something interesting that happens no matter what we do, no matter what kind of chemical reaction is taking place due to a chemical change. In all these chemical reactions, without fail, there's always some kind of starting material, which we would call the reactants, and there's always some kind of final material that we call the products. You can't have a chemical reaction without both. If you do, then you are breaking the laws of science. You can't just all of a sudden, poof, have something out of nothing. You have to have a starting material, and you have to have an ending material. Now, beyond that, there's actually quite a bit of flexibility. So we could have two things as the starting material that come together to form one thing. We could have something that starts out as two atoms bonded together and it breaks apart. We could have three things that kind of change the way that they're connected together, or even four things that essentially swap partners. There's lots and lots of different ways that we can perform chemical reactions, but one of the key things in a chemical reaction is that you're always going to have starting material and you're always going to have ending material. And not only that, the starting material and the ending material are always going to add up to the same amount of stuff. You're never going to have more stuff at the end than you did at the beginning. And by stuff, I mean like actual atoms. You're never going to have more particles or more mass at the end of a chemical reaction than you do at the beginning. This is what we call the law of conservation of mass. You can't create or destroy matter or mass. You can change the way that it's arranged, you can change the way that it is bonded to things, but you can't create or destroy it. So just like we saw here, we have atoms A and B that come together to form a molecule that is just made of those two together. We started off with A and B, and we ended with A and B, but they're just connected together differently. They're arranged differently in the product than they were in the reactant. Same thing down here. We have A, B, C, and D. And in the end, we still have A, B, C, and D. They're just connected together differently. So we can never create or destroy material in a chemical reaction. We can never create or destroy mass in a chemical reaction. And this is actually pretty handy in certain situations where if we know the amount of stuff that we started with, we know that we are required by the laws of science, by the laws of the universe, that when we finish, when the chemical reaction is done, we have to have the same mass, the same amount of stuff at the end. So in that reaction we saw a few slides ago, where we had butane burning in the lighter, if, for example, we burned 58 grams of butane with 208 grams of oxygen, that would be a total of 266 grams of stuff that reacted. If then we measure the amount of stuff that is produced, let's say, for example, we captured the water, maybe. So we had this reaction happening, and somehow we captured the water, and so we know that we produced 90 grams of water. And we know that these are the only two things that the reaction produces. Well, if we know how much water it produced, we also know that it had to have produced 266 grams of material total. Because again, because of the law of conservation of mass, whatever mass we had at the beginning, we must have the same mass at the end. And so if we had 90 grams of water, that means we are required to have produced 176 grams of carbon dioxide. It really is like a mathematical equation, essentially. So we know that we had 58 grams plus 208 grams, and that must be equal to some unknown amount of one thing plus 90 grams. And so it really is just like a mathematical equation where you would be solving for whatever that missing part was. All right, I think we'll call it there for that one. And the next one we will talk about energy, which is the last big topic of this chapter. So I'll see you there.